Guys, welcome back to my channel. And today let's look at something called W boson. Remember we are talking about boson, and we're going to examine now what is this W boson and Z boson. B-O-S-O-N, boson. Spelling can be a problem, sometimes. I was taking you through some definitions, and I think I've done quite good with you about that. Just hold on a minute. So what is boson? Sorry, I was just trying to see so that I don't repeat. I'm talking of boson. Actually, before you can go to this boson, here we are talking about subatomic particles. We are talking about quarks. What are the fundamental quarks? Are the fundamentals, quite basic state of matter. And from here we have everything like hadrons are formed, and the most stable of them are protons and neutrons. The electrons come in, forms atoms, That's a nucleon, that's proton and neutron form a nucleon. We have electrons. From there we have molecules. From molecules we have, for example, if it's dew, water. So you can see the hierarchy of how these things go on and develop matter. And actually something strange. It's not strange. It's something that is known, that if you, like what happens in sun, when you crash two photons together, you create matter. Electrons comes and some neutrinos. So we're going to go to that. So today we are going to talk about boson, which is the main force carrying energy in the universe. Okay. So the W boson is a fundamental particle. Together with the Z boson, it's responsible for the weak force. We talked about weak force. Go back the videos and you can see what weak force is. One of the four fundamental forces that govern the behavior of matter in our universe. Okay? Now, particles of matter can interact by exchanging these bosons, but only over short distances, because you can see the strong nuclear force, the weak force. These are our short range forces. They are not long distance type, they are short. They happen within the nucleus. So what's the use of W boson? Now, because they are categorized now here into two, we have W boson, we have Z boson. So now let's see what is the use of W boson. Through this force, the W boson enables the nuclear fusion reaction, nuclear fusion, F-U-S-I-O-N, reaction that powers the sun. Our sun that we use, our local star that burns up there for us to see and walk and everything, is doing just this. Nuclear fusion is taking place. And what enables that to happen is W boson. Without which life is, as we know it, will not be possible. Yeah, of course. Without the sun, what will be there? If you see the plants, photosynthesis, if you have done those experiments, quite basic, if you did science, and you see when you're putting a seed in a container and you close everything and make a small light, small cleaver is like a hole, the seed will grow towards that hole, towards where light is coming from. So it is very important. Actually, the light is so important. And as we said in the previous definition, I don't know why I defined to you. I will go back really quick. There's a place where I defined to you. Maybe it's coming. Let's go on. It could be coming. I don't know whether I'm mixing these things up. Maybe it's coming. Let's go on. The W boson is also responsible for a form of radioactivity called radioactive beta decay. Beta decay. Okay, you know, we use this quite these words, beta decay and so on. Okay, what that is. Beta is not alpha, you know, it's like the second stage of this thing, beta decay. This is the spelling of it, beta decay. Okay, it's a radioactive thing and it's called beta decay. That is widely used in medicine area. You have had radiologies, you go to people with cancers. If you get cancer, that's how they treat you, using this thing. So it's widely used in medicine. So it's very useful, if you can see. Now, what is W boson made of? You wanna know what it's made of? Already you have said what's the W boson. And if I have to repeat to you, the W boson is a fundamental particle. You know what's a particle? I've defined that to you in the previous video. Together with the Z boson, it is a response for the weak force. And you know how the weak force works? Go back to the previous videos. So what is W boson made of? It is a collision between quarks. Collision between quarks and antiquarks. That's like matter and antimatter. But quarks are not really matter. From quarks we get this, of course I told you what it is. That creates W boson. So but W bosons are created from collision between quarks and antiquarks. Now W boson decay so fast that they are impossible to measure directly. So they are not really you can't directly measure them. It's because they decay so fast. So physicists track the energy produced from their decay to measure the mass of W boson. So they indirectly they are measured. Now what's the difference between these two? We have W boson, we have Z boson. What's the difference? The two, they are charged, but they are, by the way, they are charged. They are charged. So the two W boson, the two W bosons each have a mass of about 80 GeV, C squared, giga electron volts, C squared could be that's light, where as the neutral Z boson has a mass of about 90 GeV / C squared electron volts, giga electron volts. You know what's electron and you know what's voltage. So this is the way we measure them. So we give these units to measure them: giga, mega electron volts. C squared, speed of light squared. Speed of light, C stands for constant, speed of light. It's always associated with light, actually, because if you look at this thing carefully, you see when photons is what gives you light, right? They are particles, but they travel through space carrying this energy in light waves that we see. And when you clash, you smash the two together, the electrons come out, matter now starts to come out of them. So we are measuring this like giga. We have bits in computers. When you have bits, bytes, you can go on and on, bits, bytes, megabyte, gigabyte, tetrabyte, so on. As we measure this using this, I guess that's what it is. Giga, mega electron volts. This is just a quantitative way we measure it. So in our weak interactions, W and Z bosons interact with each other, as well as with all the quarks and leptons. Interesting. Guys, if you're asking what is this weak force I'm talking about, I don't know whether I have the material around here. I could refresh your memory with it, but I mixed things up now. I don't know where there is. I kept this stuff. Wait a minute. Let's see whether I have it here, because we all know we can forget. So sometimes when I say what is this, what is this, what is that, it's quite difficult for me to, because I've already done a lot of stuff to, sorry, I have to do this. I don't know. I'm trying to find out something for you, so that we are in the same page. No way I've done this thing. I'm trying to find it. Sorry, I have to use my saliva to push the pages. Enormous, you know. We've covered quite a lot. If you are lucky, I'm gonna find it for you. If not, then we'll just go on with the video. Yeah, so here I have it. First of all, because I'm talking about a weak force, and you don't know, maybe you don't know what's a weak force, or you're watching this video for the first time, so I'm going to tell you briefly here, so that we can continue. Well, guys, I have to fix things here and there. Now, for those who don't know what a weak force is, a weak nuclear force, or just a weak force, all weak interaction. Now you see that all weak interaction, not strong, weak, acts inside of individual nucleons. And what's a nucleon? A nucleon is a proton and neutron together. I don't have to remind you this all the time. I think you know what's a nucleon by now, which means that it is even shorter range than a strong force. Of course, they're talking about the range. It is a force that allows protons to turn into neutrons. It allows protons with a positive charge to turn to a neutral state, neutrons, and vice versa through beta decay, which I wrote to you in the board just a minute ago. So that's what a weak force is. Now, an example of that, I've covered this in a video, but I'm trying to refresh your memory. The weak force, also called the weak nuclear interaction, is responsible for particle decay. Okay, this is the literal change of one type of subatomic particle into another. So, for example, a neutrino that strays close to a neutron can turn the neutron into a proton, while the neutrino becomes an electron. You see? So that's what a weak force is. So when I'm talking about weak force here, then I think we'll be together. So if we come again, because now I've talked a lot, I took a memory back. Let me come back. I was saying, what's the difference between W and Z bosons? I've given the giga electron volts, C squared. W is 80 and Z is 90 giga electron volts squared, C squared. And in a weak interaction, now what I've just told you, in a weak interaction, W and Z bosons interact with each other. See, they have different masses. Now, in this weak nuclear force that I've told you right now, these two, W and Z bosons, interact with each other, and you see their masses are different, as well as with all the quarks and leptons. You know the quarks. I've told you what the quarks are, and I don't know. Guys, I have to do this. Sorry, I have to do this because I don't have something to stick this together. I'm not so sure I'll get what I really want. Yeah. So, for example, I'm telling you this. In a weak interaction, W and Z bosons interact with each other as well as with all the quarks and leptons. You know what the quarks are, the fundamental units. Yeah, I mean, that's the basic beginning of matter. I'm not going to define everything that I tell you, but you know what quarks are. We've covered a lot about that, but you may be wondering what is leptons. So I'm going to get ahead a bit and tell you what leptons are. They are subatomic particles, such as an electron. So an electron, muon, or neutrino, which does not take part in a strong interaction. Okay, that's all it is. And what are leptons in simple terms? They are elementary particles, which means that they are not made from any smaller particles. When it's elementary, it means the last point of it. They are not made from any smaller particles. There are 6 known types of leptons, which we're going to go to come there. So I just wanted to give you basic understanding about what a lepton is. So as we proceed, you know what a lepton is, you know what a quark is. So it shouldn't confuse you. And if you don't know what a quark is, then go back to the video. There's a place where I covered that. And then go through it. Play the video and you know what a quark is. Now, why bosons are called God particles? Why are they called God particles? God particles. God. We are talking of God here. Let's find out why. The Higgs boson is better known by that's a colloquial name it was given. Means just a name. It doesn't carry any much significance. And as far as the actualization of the name is concerned, you're not saying this is God. It's just colloquial. The God particle, so called because for a generation, scientists had to take it on faith that it existed. It was on faith. It was not proven. These things are strange, you know. When belief meet with science, and you believe on something that it exists, and keep on researching and agreeing to what you believe, and eventually find it actually is like that. This is really why it's very strange sometimes that what we really have inside these heads, we carry brain inside. You know, the brain is made of tau particle. It is quite dominant there because from tau we get the DNAs, deoxynucleic acid, DNA, amino acids, which run inside your brain. So now here we think of something, and then it happens to be the real thing. Just think deeply. How is this? How is it that we think something, then it happens? It happens to be the thing. It's just some kind of intuitive intelligence that the brain itself, more cells have, that it actually connects with the entire fabric of space and the universe and reads the script of the universe without you knowing subconsciously, and gives you the right thing about what it is. So since we are connected the fields, since we are made from these fields, the electrons, the quarks, is there a way our brain connects without us even knowing? Because look, we are using 3% of our brain, 97% is untapped. Do we know really that is untapped, or is at work with the invisible world that we are not aware of? I'm trying to see the connection between this, that this thing was taken on faith, and it really existed. Isn't that strange? Okay, now why is W boson in beta decay? I've told you what a beta decay is, not alpha, beta decay. Let's not go on, keep on going back, because we'll not really be able to cover much. If you don't know what's a beta decay, you can. I made video on beta decay, so you can go through that. It's the second stage. Decay means radiation, not that in the very beginning. Sorry, I'm taking water. You're talking about lorry here. So, why is W boson a beta decay? In a beta decay, a neutron composed of two down quarks. Of course, a neutron has got two down quarks and one up quark, and one up quark decay to a proton composed of a down quark and two up quarks. Decay means gizzard radiation. Now, in the process, an antineutrino and an electron are emitted. This is what I was telling you before. In the process of this decay, radiation, now something's formed here called antineutrino and an electron. See, now electron is matter itself. The W boson is the mediator for the transformation of a down quark into an up quark. It's the mediator, it's the go-between these two. It's what makes them change their forms instead. And that's why I was saying actually that was my own basic theory, and nobody's saying this. It's my thinking, and I may be right about this, that there is a state in nature below which something does not go. Like a constant. I'm going to talk about cosmology. These are universal constants. Actually, there is a state where when it reaches that stage, whatever you're dealing with turns to another form. So it doesn't go below that. There's no, like there is a ceiling, a limit. It can't go beyond that. Because like here in this case, we are talking of a boson in a beta decay. Here we are talking of antineutrino and an electron getting emitted. So what are the processes taking place here? What are the chemical processes taking place here? What is this interaction? They are giving the reason why W boson in a beta. Why is it in a beta decay? In a beta decay, a neutron, composed of two down quarks and an up quark, decay. They decay to a proton composed of a down quark and two up quarks. They change into a state when they are in this beta decay state. I don't know what I can find in this thing. It's gonna be really a lot of work for me to trace this thing, because anyway, in the future videos I give you the reference about more details about beta decay. But it's a stage. Now, like when you're boiling water, a very good example I gave in the other video. At some point it's ice, then it becomes liquid. Then when you boil it, it becomes vapor. It vaporizes, and then it can condense and come back down like a liquid. You see, it's going round, so it's changing from one state to another. And that's why I'm saying this is all matter. It's all matter. So the W boson is the mediator of these two. Now I'm going to tell you, actually I was talking about GeV/c square root. It means a giga electron volts. Giga or giga, I don't know how you can pronounce it. I'm going to write it for you. GeV. This is the way I read G. By the way, I mean this in small letter. I mean G. This is G. Then we have E V C squared. This thing, it means giga electron volts divided by the speed of light. Yeah, I was right. This is divided by the speed of light. Giga electron volt divided by the speed of light squared. Now, electron volts is a measure of energy. Electron volts is a measure of energy, EV, and is the energy gained by an electron crossing a potential of 1 volt. 1 EV, electron volts, equal to 1.6 times 10 raised to the power minus 19 joules, which I've already told you. So 1 GeV is equal to 1.6 times 10 raised to the power minus 10 joules. So now you know what a GE is. I'm trying to make it very simple for you to understand. So when I'm saying that what's the difference between W and Z bosons, for example, we are saying that the two they are charged particles. The two charged. In parentheses, it's written charged, where W boson each have a mass of about 80 GeV/c squared. Now I've told you what GE is. GE means a giga electron volts divided by the speed of light. And the electron volt is further defined a measure of energy, and is the energy gained by an electron crossing a potential 1 volt. So yeah, that's it. I don't know whether we should go on, because it might be too lengthy video for you guys. Maybe I'm gonna tell you just a gluon and we'll stop it there. Now, what is a gluon? Gluon, G-U-L-U-O-N, gluon. We have to give them names, guys. You know, you don't call them these names. How do we differentiate them? Gluons. This is the name. Gluons. They are particles, of course. They are particles with different mass, different energy states. Yeah, given these names. Make my throat. What is a gluon? It is a type of elementary particle that mediates the strong interaction between quarks. Not weak interaction, strong interaction between quarks. And the word quark is strong, by the way, very important. We're gonna see it. Acting as the exchange particle for the interaction. It's like a medium through which, like if there are two states like this, and this is a medium. So this is a gluon. It is mediating between, say, let's here. These are quarks, between quarks, and acting as exchange particles for the interacting. So what is a gluon? It's a type of elementary particle that mediates the strong interaction between quarks. We have two up quark, one down quark, two up quark, or one up quark, two down quark. So this thing called gluon is what mediates it, this exchange. And the gluons are they act as exchange particle for this interaction to take place. So they are like a medium through which this interaction takes place. They enable this thing to happen. So gluons are massless vector bosons, thereby having a spin of 1. Okay, they have a spin of 1. I've told you what 1 have integer spin, full integer spin. So guys, let's end this video here for today, and we'll proceed defining what these things are. What are the quarks? What are the prions soon enough. Now we are dealing with the bosons. We're gonna go to the last point of it. So we are still now. Next we talk about the muons, so stay tuned as we go through this. And I have a diagram here which I've drawn to illustrate these things. I'm going to show you more about it in the next video. Like, please share and subscribe to my channel and comment, give your ideas. You give ideas, don't just watch. You have to think. Bye for now. See you later. Bye.